For part 2 of angular kinematics, we are going to discuss angular, tangential, and centripetal acceleration, and then discuss importance of identifying planes and axes of anatomical position, specifically related to rotation in anatomical movement. So angular acceleration is defined as the rate of change of angular velocity, and this is representative of starts, stops, if something is speeding up, slowing down, or if there is a change in axis of rotation. So mathematically, angular acceleration is equal to alpha equals change in omega, or angular velocity, divided by change in time, which can be further explained by omega f minus omega I. So final angular velocity minus initial angular velocity over the change in time of a movement. Now, angular acceleration can be represented by radians per second squared or degrees per second squared, dependent upon the situation that you are given and the problem that you are asked to solve. So direction of angular velocity relative to angular acceleration follows the right-hand rule. So these two variables are dependent upon how we define the planes and axis of rotation and use the right-hand rule to determine the direction in which these two variables are going. So again, angular acceleration occurs when something is speeding up or starting, and angular acceleration in this case is in the direction of angular motion. If an object is slowing down or stopping, then angular acceleration is in the opposite direction of angular motion. So, if the sign of velocity and the sign of acceleration, being positive or negative, are the same, the body is rotating faster and faster or speeding up. If the sign of velocity and sign of acceleration are opposite, the body is then rotating slower or slowing down. From these conceptual components, we know that when angular velocity, or omega, increases, the tangential velocity of points on the body actually increase. Now, tangential acceleration is defined as the component of linear acceleration tangential to a circular path. So tangential is meaning if you have a circular path that an object is rotating around, the tangent to this is going to be a point that is ultimately going to be a linear representation of where the object would go if it were to release from this circular path. Centripetal or radial acceleration is defined as the component of linear acceleration towards the center or the radius of the circular path. So centripetal or radial acceleration is directed directly towards the axis of rotation. If we look at this depiction here, we can see a better representation of what tangential acceleration would look like and centripetal acceleration. Now, centripetal acceleration occurs because there is a force pulling inwards towards the axis of rotation, and we will discuss these two components further in the next couple of slides. So again, tangential acceleration is the component of linear acceleration tangent to the circular path. So linear acceleration is occurring because there is a change in linear velocity due to the constant change in direction. This change in direction occurs due to a force that is pulling inwards towards the axis of rotation, which, as I said in the previous slide, is represented by centripetal acceleration. So mathematically, we can define tangential acceleration as a sub t equal to alpha, or angular acceleration, times the radius of acceleration. So alpha sub t is instantaneous tangential acceleration, or the tangential acceleration at one instant in one spot of that circular path. And alpha is angular acceleration that, again, is instantaneous. And what is important about tangential acceleration relative to angular acceleration is that angular acceleration must be represented by radians per second squared. So if you are given a problem in which you know the degrees per second, or the degrees per second squared, and you are asked to solve the tangential acceleration, you must first convert degrees per second squared to radians per second squared in order to accurately solve the problem. Because we know that linear acceleration occurs when an object slows down, speeds up, or changes direction, we can apply this to angular by the v sub t, or tangential velocity of an object moving on a circular path at a constant angular velocity changes direction from point to point. If it is released at different points on the path, the object will travel linearly in different directions. So if I draw my circular path, well, that was bad. My circular path here, if the object was rotating in a clockwise direction and it was released here, it would go in this direction. But if it was released on the other side of the circle, it would go in a very different direction. So centripetal or radial acceleration is acceleration directed directly towards the axis of rotation, or the center of the circular path, and it is caused by the centripetal force that is pulling inwards towards the center of the path. Now, there are two equations for centripetal or radial acceleration. One is related to tangential velocity, the other is related to angular velocity. Radial acceleration related to angular velocity is mathematically expressed as a sub r equals the radius times omega, or angular velocity. So from this mathematical expression, we know that radial acceleration is directly related to angular velocity and the radius by which something is rotating. So we know that radial acceleration will increase if r increases, or if omega, or angular velocity, increases. Radial acceleration related to tangential velocity is represented by a sub r is equal to the tangential velocity squared over r. So in this case, the radial acceleration relative to tangential velocity, conceptually, or the relationship between the two, is a little bit different. Because in this case, because we are dividing by r, if r goes down, then radial acceleration is going to increase. If r increases, then radial acceleration is going to decrease. So, if angular velocity is constant, radial acceleration is directly proportional to the radius. If tangential velocity is constant, radial acceleration is inversely proportional to the radius. An example of this is having two track athletes running around a standard track. So a runner in the inside lane has to exert more centripetal force via friction than a runner in the outside lane if both runners have the same linear velocity. The centripetal acceleration of the runner in the inside lane is greater because of the smaller radius. In the next few slides, we're going to hopefully describe what would be a review for you all of defining motion by planes and axes so that we can more accurately standardize and describe these motions on one level. So we know that the anatomical position is standing upright, facing forward, feet aligned with toes forward, arms hanging straight by the sides, and palms facing forward with fingers extended. This is a good depiction of the cardinal anatomical planes and axes of the body. So we have the three main planes: the transverse plane, the sagittal plane, and the frontal plane. Transverse plane is going to divide the body in top and bottom halves. Frontal plane is going to divide the body in front and back, or anterior posterior. Sagittal is going to divide right and left. Now the longitudinal axis here, the transverse axis and the anterior posterior axis, are also extremely important because these axes are going to be the point at which some anatomical segment moves about. Alright, so what's extremely important to remember is that motion occurs within a plane and about an axis, and that will not be the last time you hear me say that in this lecture. So to review, sagittal plane runs anterior to posterior, front to back, and superior to inferior, top to bottom. It divides the body into right and left parts. Frontal plane, or also known as the coronal plane, divides the body into anterior and posterior parts. Transverse plane divides the body into superior and inferior parts. Anatomical axes. The anterior posterior axis is the imaginary line running from anterior to posterior and is perpendicular to the frontal plane. The transverse axis is the line running from left to right and is perpendicular to the sagittal plane, and the longitudinal axis is the imaginary line running superior to inferior and is perpendicular to the transverse plane. So here we have a couple of, or an example of each of these. Cartwheeling is a motion that is about the anterior posterior axis within the frontal plane. Somersaulting is about the transverse axis and within the sagittal plane. And twisting, like as if you were twisting your torso or your spine, is about the longitudinal axis and occurs within the transverse plane. So again, a segment moves within a plane and rotates around or about an axis, and the plane of motion and axis of rotation are always perpendicular. Joint actions are typically described as relative angular motion. So we have one segment relative to the other, or for example, the forearm relative to the humerus. So this is motion between two segments on opposite sides of a joint. Within these last slides, I'm going to give you specific anatomical movements that are known to be within a specific plane and about a specific axis. So within the sagittal plane and about the transverse axis, we know that flexion, extension occurs, hyperextension, and dorsiflexion or plantar flexion always move within the sagittal plane and about the transverse axis. In the frontal plane, about the anterior-posterior axis, we have abduction, adduction, radial and ulnar deviation, inversion and eversion of the foot, elevation and depression of the shoulders, and lateral flexion to the left or lateral flexion to the right of the trunk. Within the transverse plane and around the vertical axis, We have internal and external rotation of the leg or the arm, pronation or supination of the palm, horizontal abduction or adduction, and rotation left or right for the head, neck, or trunk. Circumduction, however, encompasses multiple axes joint actions around the transverse and anterior posterior axes. This segment motion forms a cone-shaped surface. Okay, so it is going to combine multiple axes of rotation and could encompass multiple planes of motion.